There are a couple of scenarios where the methodology for paired or dependent samples is appropriate. The second one is the more intuitive one, where there are actual pairs of individuals. However, that one's not the most common. The first one is. That's why it's in bold. Usually it's a bunch of individuals who have two measurements, and that's how you naturally get the idea of pairing. You have two measurements pairing up to a single individual. And the idea of a before and after measurement of some kind is pretty typical. There is some new notation toward the bottom of the slide. It looks pretty close to what you'd have for the notation for a single mean, except for those subscripted D's that are supposed to represent difference. What we end up doing from a procedural standpoint is exactly the same thing that you do for a single mean, except that you treat the difference like it's a variable. Conditions for inference: first of all, you need to have paired data for this idea to work. But then if you look at what's below that, it's the same stuff that you'd have for a single mean, except that it has an n sub d instead of an n in those bullet points. So if n sub d, the number of differences, is at least 30, you can apply the central limit theorem. If n sub d is less than 30, either take a look at the shape of the distribution of sample differences to make sure it's symmetric and single-peaked with no outliers, or if your n sub d is really tiny, by which I mean less than about 15 or so, if you want to proceed with the methodology in Chapter 6, you'd have to blindly assume that the population is normally distributed. If your number of differences is that small, then if you tried to make a histogram or a dot plot out of a sample that small, you don't get much of a shape with only 12 or so points. It would be hard to tell if you had something that was symmetric and single-peaked and that sort of thing. That's why that's in there, just in case of n sub d being very small, where graphing the sample might not really give you anything usable. And if either of those above cases are satisfied, then you would find p-values and critical values using a t-distribution with n sub d minus 1 degrees of freedom. Down below, looking at what we have for the sampling distribution, the confidence interval formula, and the test statistic formula, they're basically the same stuff that you have for a single mean, just with subscripted d's. Except for the case of the test statistic, the value from the null hypothesis automatically is 0. It doesn't have to be that, but that's by far the most conventional thing to do here, where if you're going to have a hypothesis test, you're looking for evidence of either a difference or an increase or a decrease. If you're doing any of those things, the value that's in the null hypothesis and the alternative hypothesis, the numerical value, is 0. For this example, where we have scores on a math aptitude test before and after taking a training course, going forward, to find the confidence interval, the only column that matters is the difference column. We're going to treat the difference like it's the variable, so the specific numbers of the before and after columns don't really matter after we have the differences computed. Then we can just focus on those. The first thing is to see if we can apply the central limit theorem, and if not, what we're going to have to do. Well, the sample size here is 10 because it's the number of differences. So it's 10, not 20. This is the common mistake with the paired sample material. The common mistake is to count up the total number of observations, which in this case would be 20 because you have 10 before observations and 10 after observations. But if we're going to treat the difference like it's the variable, we have 10 differences, so n sub d is 10. That's pretty small. That's one where we certainly can't apply the central limit theorem, and that's too small to look at a histogram. So in order to go forward, we're going to have to assume that the population is normally distributed. Here, that would be the distribution of differences. That's the thing that we're treating like it's the variable. That's why that's underlined, just to emphasize that. To get the critical value, if n sub d is 10, we need to use 9 degrees of freedom and 90% confidence, so we need a 0.9 in the center, so our critical value is 1.833. There's the computation of the confidence interval, which already shows up in the notes, and we end up with a confidence interval that's entirely positive. To answer that question toward the bottom of the screen, the answer is yes, because the way that we set up the difference was as after minus before. Positive values would indicate the average after score being higher than the average before score. So since the whole interval consists of positive values, then we can say yes, that it looks like there's been an increase in the mean score. In this hypothesis test example about heart rate and chewing tobacco, n sub d is 48, so that's large enough to apply the central limit theorem. The number of differences is equal to the number of users because this is again a scenario where we have two measurements for each user, so we get one difference for each user. And if the order of subtraction is after minus before, that'll dictate, I suppose, the sign of x bar sub d and the direction of the inequality in the alternative hypothesis. Because if we're looking for an increase, like it says up in the paragraph at the top, then if that's the order of subtraction, we're looking for evidence that mu sub d is positive, that the after measurements are on average higher than the before measurements. And that would be a positive value with that order of subtraction. This is all in the notes, but I think we can run through it pretty quickly. If n sub d is 48, we need to use a t-distribution with 47 degrees of freedom to find the p-value. The mean will be 0 since that's what's in the null hypothesis. And the standard error of the sampling distribution, just using the given values, we can compute it to be 0.4431. The test statistic, it'll be 3.75 minus 0 divided by that standard error. And to 3 places, it's 8.463 if you don't round off any intermediate steps. The p-value would be the probability of getting an x bar sub d of at least the one that we got, at least 3.75, which would be the same thing as the probability of getting a test statistic of at least 8.463. Using stat key, you get a p-value of 0. We'll see that on the next slide. The reason I put in the R computation of the p-value is to point out that the p-value isn't really 0. It's just 0 rounded to 3 places. When you use the approximation method, so if you're using a normal distribution or a t-distribution to compute a p-value, you never get exactly 0, but you'll get values that are so tiny that they're going to round down to 0 if you use stat key. And that's what's happening here. There's the p-value from stat key. It's a right tail if you look in the upper left corner. That's what I have selected. And then the cutoff needs to be 8.463 since that was our test statistic. And then you can see my degrees of freedom of 47 in the upper right corner. So if the p-value is 0 or something that's very, very close to 0, it's certainly going to be less than 0.05. So we should reject the null. That means that there is sufficient evidence to conclude what's in the alternative hypothesis, that using chewing tobacco increases the mean heart rate of all users.